본격적인 포럼 시작해 보도록 하겠습니다. 먼저 첫 번째 기조 강연이 기다리고 있는데요. 이 기조 강연의 주제는 게임 체인저가 된 양자컴퓨터입니다. 대담자가 또 준비를 하고 계시죠. 이준구 카이스트 인공지능 양자컴퓨팅 ITRC 센터장께서 함께해 주시겠고요. 그리고 로버트 슈터 IBM 퀀텀 총괄부사장께서 강연에 수고를 해 주시겠습니다. 강연에 수고해 주실 로버트 슈터 총괄 부사장님은 35년이 넘게 IT 업계에 종사를 하면서 기술 리더 겸 임원으로 또 활동을 하셨는데요. 그중에 20년 이상은 뉴욕에 위치한 IBM 리서치에 근무하시면서 양자 컴퓨팅, AI, 그리고 블록체인, 애널리틱스, 빅데이터, 그리고 모바일, 소프트웨어 관리 및 개발과 기술 전략 등 다양한 분야를 연구를 하셨습니다. 자, 첫 번째 기조 강연 굉장히 기대가 되는데요. 대담 진행해 주실 이준구 카이스트 인공지능 양자컴퓨팅 ITRC 센터장님 단상에 나와 계십니다. 저는 마이크를 센터장님께 넘기도록 하겠습니다. 부탁드리겠습니다.
네, 감사합니다. 카이스트의 IT 연구센터 중 AI 양자 컴퓨팅 ITRC 센터를 리드하고 있는 이준구입니다. 오늘 이런 그 사이버 스페이스에서 이 포럼을 하게 된 것을 매우 새로운 경험으로 가지고 있습니다. So I'm going to change my the mode of my language because I have to introduce Dr. Bob Suter for the presentations. So Bob Suter has been leading the IBM Q, which is quantum computing development and researches, and he where IBM introduced the quantum cloud service in year 2016, and that has been a great success that fostered the whole community of quantum computing to have a real experience with the quantum computers. Now, today, Dr. Bob Suter will discuss about his presentation about the quantum computers development at IBM researches. So I'd like to pass this to Dr. Bob Suter for his keynote speech for the forum. Okay.
Thank you, and good morning. I'm pleased to join you this morning as one of the leaders of the IBM Quantum program. I'm in New York this morning. You may see my New York Yankees cap. Unfortunately, we have no baseball in the United States, but I'll talk about quantum computing instead. Let me start by saying that I think quantum computing will be one of the most important computing technologies in the 21st century. And so what I'm going to do is try to give you some evidence that we have made very strong progress on quantum computing so far. So first of all, at a very high level, what is quantum computing? Well, one way to think about it is that nature itself is one great big computer. Now, it's not a binary computer. It's not a digital computer like we're used to, such as your phone or your laptop, or even the supercomputers of the world. But if you think about it, nature carries with it and processes a tremendous amount of information and data. So that's computation in a way. Now, technically, quantum computing is based on part of physics called quantum mechanics, and that goes back to the early 1900s. Well, what we're trying to do with quantum computing is to learn if we can harness this power of physics, of nature itself as a giant computer, to help solve some of the very hardest problems that we have. So quantum computing is nature-inspired, but quantum computing itself requires actual hardware. If you don't have hardware, if you don't have quantum computers, you are not doing quantum computing. So let me give you 3 examples of where we believe now, we the industry believe, that quantum computing will be able to help. And the first is around chemistry. Now, this makes sense because, as I mentioned, quantum computing is based on quantum mechanics, which rules or is the model for very small things, such as electrons or atoms or molecules, and molecular reactions, such as those around us, in our bodies, everywhere in the universe, drive what we see and think is the universe. So if we can exactly model atoms and molecular reactions inside a computer, inside a quantum computer, it means we may be able to do some things much, much faster than doing it in a laboratory itself. Now, I do want to say that quantum computers today are not powerful enough to do anything whatsoever with COVID or the coronavirus. We are at the very beginning stages for quantum computing. We will not be able to deal with molecular reactions that involve molecules so large for 10 or 15 years, sometime in the future. But this is an early first application for chemistry, for new materials that we hope to apply quantum computing. The second area is in financial services. Of course, many people are interested in financial services, in business, but also for their own self-economics, their home, their family. Well, we can do many things with very large computers, high-performance computers. But there are some limitations, and these limitations tend to come up when we are trying to get calculations, such as doing a risk assessment on a portfolio of stocks and bonds, financial instruments, or if you were building a factory, any sort of manufacturing, for example. You're limited today by what you can do, and it's only an approximation to certain levels of accuracy. So we hope to be able to do simulations significantly faster. Now, I don't just mean 2 times faster, because if you want to do something 2 times faster, just wait a little while. The computing we have today, what we call classical computing, will catch up and will do what you want. So we want to be able to tackle problems that are really much, much, much larger. We want to get much better accuracy. Of course, we would like to do it faster, and we would like to do all of this computation for whatever we're trying to accomplish much less expensively. And the third area is artificial intelligence or machine learning. Well, this is a secret about artificial intelligence and machine learning. Way down deep, when you get underneath it all, yes, there's a lot of data, but it's mathematics that drives. So, will we be able to do the mathematics underlying artificial intelligence faster? Will we be able to use the unique properties of quantum computing to find patterns in new ways that we cannot easily do with the classical methods that are in use today? Now, one of the features of quantum computing is it has what's called exponential growth. There are situations where as you add more and more information units, what we call qubits, you double the amount of information you can process. This is exponential. You're constantly doubling 2, 4, 8, 16, 32, and so on. Well, can we use this type of good growth in quantum computing to control the growth that happens in some problems when we don't want it to? Or eventually, if we have data that has so many different dimensions, what we call features, can we control this? Can we process it better? So as was mentioned before, IBM first put up a quantum computer on the cloud in 2016. And this was a 5-qubit quantum computer. And a qubit, as I mentioned, is the basic unit of quantum information. Now, I must say now, I do work for IBM. I am part of our quantum program. I do very much believe that by any metric, we have the largest program, the longest running program available. So I am not trying to make this sound like marketing, but I will use our experience as the proof points to tell you how far we've come. So what this means, if we started in 2016, in fact, the 4th of May, 2016, is that we as an industry, and IBM in particular, are now in our 5th year of providing quantum computers on the cloud. So quantum computing is coming along, but it's not exactly new. And this is what I think I would really like you to understand, that it is now time for people to start thinking about the use cases they will like to have for quantum computing in the future. It will be several years before quantum computers are powerful enough to do anything better than what our classical computers can do today. So what this means is that the return on investment may be several years away, but because quantum computing is so different, we as an industry, you as people who will use quantum computers, right, need to learn how to harness this power and apply it to the problems that are of interest to you. So some statistics after 4 years. And once again, I want to show this as evidence that many people are using quantum computers today. We have, for our program, had over 230,000 registered users. We have had those people in their work, and this is through our absolutely free quantum computers or the commercial program called the IBM Q Network, run over 180 billion circuits on 18 computers. That's how many computers we have on the cloud today. So as I said, we're near the beginning, but we are not at the beginning. Think of a circuit as the basic unit of work. And so when someone runs a circuit, it means they are telling a quantum computer to do a specific task, perhaps part of an algorithm. And so put that way, users have run over 180 billion quantum tasks on real hardware. So that is progress. So this is a little bit about the history and where we're going. So first of all, quantum science, quantum mechanics goes way back to the early 1900s. And these were names like Einstein and Bohr and Dirac, Heisenberg, physicists, famous physicists from the beginning part of the 20th century. Quantum advantage is where we're trying to get to. That will come, we believe, in the later part of this decade. And that is when quantum computers will do things significantly better than just classical systems, your phone, your laptop, the supercomputers that we have today. So in the meanwhile, we are getting quantum ready. We all are learning about quantum computers. We're engaging with people. We're thinking about use cases. And so we're getting ready to take advantage of these quantum computers. Now, if you wish, you can be using a real quantum computer in about 5 minutes. I would ask maybe you wait till I stop speaking, but if you wish, you can go to the IBM Quantum Experience right now, and you can use real quantum hardware at no charge. You can start learning, you can start experimenting, and I do encourage many people to do that. As I've said before, nearly 250,000 people are already using real quantum computers. And this is the best way to get some hands-on experience to try to do this. But if you think of it from our part, how can we encourage people to learn about quantum? It has a reputation for being a little bit like science fiction. It has a reputation for being a little bit hard. Is it too hard? Is it not possible to attract people to learn about this? Well, again, I'm going to give you some evidence that maybe it's not. So for the 4th anniversary of our putting a quantum computer on the cloud, and on the right-hand side, you see a model of a 50-qubit quantum computer. We ran a challenge over 4 days, and this was at the beginning of May. And these were 4 problems that got harder and harder and harder. If you had any interest in mathematics, you could do the first problem. After that, you had to know a little bit more, or you had to learn a little bit more. So this was a very directed way of having people come and use quantum computers, learn a little bit about, and to have that be the foundation. And we invited many people, such as students, the people who had been working with us, developers, but we hoped that many people from many companies around the world, people who are companies who are wondering when quantum will be ready for them. Well, this challenge allowed some of your employees to learn more about this. So it ran for 4 days. Well, we did this to demonstrate how easy it was to use real quantum hardware. The other situation is, of course, many of us are sitting in our homes and have been in our homes for months and months and months. We're not around groups of people with whom we work or collaborate as much. So we want to give a fun but seriously educational experience that people could do by themselves. Yet they could still use tools to collaborate with their friends, such as Slack, Twitter, other social media. Gave people access to the completely free and online QuizKit textbook. QuizKit is the programming language that people use. And we introduced this concept of circuit that I mentioned before as the basic unit for quantum computing. Well, how did we do? Remember, 4 days, and we opened it up to people all around the world. We had participants from 45 countries for the challenge, including, of course, Korea. In total, we had 1,745 people work on these problems. So think about that. If you were wondering how many people know anything about quantum computing, well, I mentioned some very big numbers before, but we managed to get nearly 2,000 people come and work on these problems for fun. Many people stayed up all night, particularly on problem number 4, which was a real challenge. Yet 574 people solved all 4 problems, including the 4th one. And I will tell you a little story, which is we knew what we thought was the correct answer. And to do problem number 4, you had to see how close you could get. Well, interestingly, 4 people around the world got a slightly better answer than we did. And so it shows how many smart and clever people. We now know how they did it. And we, in fact, have posted a video explaining their methods. During this time, for the challenge and for our regular users, people ran over 1 billion hardware quantum circuits. They ran over 1 billion tasks on real quantum hardware a day for 4 days. Now, this wasn't the first day. There were a couple of other days before that we had run over 1 billion, but for 4 consecutive days. So in some sense, maybe it was a world record, but it was also historic. We broke the 1 billion circuit barrier, which shows we have a lot of momentum and good progress on quantum computing. Now I want to really finish up today by talking a little bit more about the business side of this. We are not doing quantum computing just for the fun, just for the science. We are doing quantum computing in order to enable new computation for the future for businesses and for organizations. Well, we at IBM, we do have very large teams of people working on quantum computing, but we can't work on every problem. So at the end of 2017, we began the IBM Q Network to bring together large companies, universities that worked with smaller companies in the regions, startups, many different types of organizations that wanted to start getting involved and drive the research for real business use cases. And this was the IBM Q Network. So the end of 2017, so about 2.5 years ago. At this point, we have about 106 members. We're always getting more, so this is a relatively accurate. You can see our industry partners on the left-hand side, companies like Daimler, like Samsung, of course, ExxonMobil, banking, JP Morgan Chase, Accenture as a system integrators, Goldman Sachs, Woodside Energy in Australia, BP, Amgen, and even Boeing. Boeing, which is based in Seattle, along with, I will say, 2 of our competitors. Our hubs are universities or their government labs that want to work with local industries. The very first hub was Keio University in Tokyo, but I'd also like to highlight Oak Ridge National Lab in the United States. It's a Department of Energy hub. And they then serve other United States Department of Energy laboratories, such as Fermilab, Argonne, Brookhaven, and so forth. Many, many startups, because if you're starting a company about quantum computing, you should use a real quantum computer, and that's what we can provide. And then many academic partners that are with us either for research or for education. And that's so important. We must teach the people who are in college and university today about quantum computing so that they can become the employees in the future that help organizations and businesses make it successful for them. So I'm going to just stop here with this invitation and with this question, which is, have you accessed IBM Quantum on the IBM Cloud yet? That's the link. As I said, it would take you about 5 minutes to start using a real quantum computer. Whatever you do, it's time. It's time to learn more about this technology. It's time to think about how it may be useful for you in this decade, later in this decade. It's time to think about, who do you have to advise you? Who works for you who can champion this new type of technology. So with that, thank you very much. And I believe we'll continue on to a conversation now about quantum computing.
Well, thank you very much. That was very exciting, presentation of the quantum computing of the state of the art of today. So let me start with some questions that came from one of the netizens. Within Korea, we use the word netizen very often. That means people that who are active on the internet, the social media networks. So one of the you're right. So the first question is basically coming from one of the students who try to teach, who is studying for the education in physics. And his question was, first of all, what is quantum, right? You wrote a great book, The Dancing with the Qubits. Actually, I like it, and actually, that's a great book to read. And could you just briefly explain the concept of quantum that was,
Yes.
discussed in your book together? Yeah.
Sure. Well, as I mentioned, we have this idea of a qubit or a quantum bit. And the title of my book is Dancing with Qubits, which is a little bit of a strange title until you learn a little bit more about quantum computing. If we think about classical computing, the basic unit of information is the bit. And a bit can be 0 or 1. And so when anyone says anything like computing is just many zeros and ones, that's what they mean. Well, for us with quantum, we have a more powerful basic unit, and that is, again, what's called a qubit. A qubit does not only take those two numbers, 0 and 1, on when it is working. And this is where we get a little bit more mathematical. While a quantum computer is working, a qubit can take on a two-dimensional space worth of values, which is one way to think about it. So if you remember, perhaps from geography, what we would call X and Y, the horizontal and the vertical axis, or if you think of a map and you think of latitude and longitude, right? Somehow you have two numbers to represent this. Well, the magic happens when we start using more qubits. And so 2 qubits can represent two numbers. Excuse me, 1 qubit can represent 2 numbers. 2 qubits can represent 4. But then when we go to 3 qubits, we can represent 8. That's 2 times 2 times 2. And so this quickly scales. By the time we get to 10 qubits, the number of pieces of information we can represent are over 1,000. By the time we get to 300 qubits, so if we had a quantum computer with very good qubits, and I will leave that undefined, what very good means here, but if we had 300 very good qubits, the amount of information that that quantum computer could represent in the middle of a calculation is more than the number of atoms in the universe that we can observe. Now, in many ways, that's ridiculous. How can we do that? Right? Well, that's because quantum computing is based on nature. And so we get terms like superposition and entanglement. Entanglement is what causes this magic, which is getting more and more and more. The name of my book comes from one time when I described the way the qubits work together in an algorithm to solve a problem is almost like a dance. They come together, they accomplish something, they do something else, and they move on. So this is the dancing with qubits. But it is all this which potentially gives so much more computing power for some types of problems.
That's the amazing power of the quantum computation. Wow, that's great. IBM has been leading the whole community as the first mover for the last maybe 20 years. That has been a long while. And for the last several years, actually, after introduction of the quantum experience, we have, you have created a lot of research results. Even for myself, I'm using quantum experience to write my several papers of mine, and I really appreciate such kind of the services to the public, right? But from your experience in the past, okay, could you share what has been really observed from your clients, not just from the general public? I think you have very close the clients that works with you, like some partners level. Is there any possible discussions that you can share with your experience to the public?
Well, I think there's some interesting areas. On one of the slides, though I did not mention it, when I was talking about chemistry, we have been working with companies like Daimler, Mercedes-Benz, as well as Mitsubishi Chemical, to create better lithium batteries. Because whether it's electric cars, whether it's other things that are powered by electricity, we must have much more efficient batteries. We need them 10 times better, perhaps eventually 100 times better, right? It's very costly to do this physical research, this physical chemistry. So if we could model the chemical reactions that happen in the various types of lithium batteries, and there are several kinds, inside a computer, it could speed up the research to put into the hands of people these better batteries, and therefore cars and other devices, right, that last much longer. You would expect a company like JP Morgan Chase would be working on financial services types of applications. Many people are interested in artificial intelligence, though we are very early, I must say, with that. The artificial intelligence is getting more and more powerful and more widely used, but as it does, it is using a lot of the computational power that we have. And so certainly we can have better classical algorithms. We can have specialized artificial intelligence hardware. But if we can also in the future use quantum computing to do artificial intelligence better, if we can train models faster, if we can make those decisions faster, then that will be a win. One thing I do want to warn is that quantum computers cannot now process a lot of data, right? If you ever see an article that says the world is creating many petabytes of information every day, thank goodness we have quantum computers, please stop reading. Quantum computing is about computation and not data processing. But as I said in my talk, at the heart of AI is mathematics and computation. So we are hopeful.
That's excuse me. Okay, excuse me. So that's a great side, the optimistic side of the discussions. So, well, there are a lot of optimisms and pessimisms of this new technology. And could you briefly, say what could be the optimistic, scenarios for the vision, and what could be, most pessimistic scenarios for the vision for the next 10 or 20 years, something like that?
Well, I mentioned this idea of a qubit as this basic unit of quantum information. The fundamental question is, how do you make a qubit? And there are different ways of doing. We do what are called superconducting qubits, as does Google. Other people are looking at ion traps. Other people are looking at those related to light. photonics. We, as you would expect, think that ours is the right approach. But what everybody will have to deal with is to move from quantum computers where we have 20, 30, 50, even low 100 numbers of qubits, eventually to thousands and thousands and thousands of qubits. So the optimism is that we have made very good progress over the last, let's say, 10 years, right? Particularly with superconducting. But the place where we need a lot more science and a lot more engineering is how we will scale, how we will go from where we are today to having much bigger, much more powerful machines. Interestingly, our types of qubits need to be cooled down close to absolute zero, very cold. That is not a special problem. Whether we'll eventually have room temperature or very cold qubits, that's not so much a problem. It's just being able to get many qubits that can work together to allow us to get this full power from the machines that we will need.
That's okay. I agree that the temperature is not the real problem. I really appreciate the possibility of creating multiple, as many as possible, qubits in one system. So when do you think we are going to beat the capacity of supercomputers?
Well, that's the big question, and that's the question when we will see quantum advantage.
Yes.
So quantum computers will change significantly over the next 10 years. Today, we are in the era of what we call noisy quantum computers. And we need certain kinds of algorithms to work today. Nevertheless, we are very hopeful for roughly 5 or 6 years to see the very first examples where quantum computers can do better than classical computers. There may not be many of those examples, but I'm just saying the very first ones. But at the same time, our hardware will be improving. And when we get to 10 years and 15 years, we will have things called fault tolerance, error correction. That will change the types of algorithms we can use. If we get this to scale up to many, many qubits, then we can tackle other problems. So it's interesting that we keep trying to find the answer to when we will have this breakthrough, or quantum advantage, while everything is changing constantly. So it's not a static prediction, right? There's much science and whatever. So let me say the second half of this decade, if I want to be safe.
Okay, that's not too long, actually.
No.
It's on the horizon that we can see. Right. Okay. I'm just turning back to another, pessimistic side. So, will there be any showstopper in your mind?
I don't see them as showstoppers right now. I think there are things we have to work through. So we mentioned scalability, which at the simplest level is saying go from a few qubits to many, many. Well, that's easy to say, but will be hard to do necessarily. So how can we get that many qubits talking to each other, right? How can we get the full power of this entanglement, this dance, as I called it before, with so many qubits to take full advantage of the machines? Will we need to eventually go to multiple quantum computers that are connected to each other? How will we do that, right? will we be able to find increasingly efficient algorithms, right, for the right types of problems? Will we discover that, in fact, things may take slightly longer because we will need error correction to really do what we want to do? So I don't term them as showstoppers right now. There's nothing we look at and say, oh, that's a major problem, that's impossible. It's just there are significant scientific and engineering problems. Let me, though, draw an analogy. If I go back and I look at a television that I in the United States might have bought 15 years ago, it would have been a very big and heavy television. It would have been a tube television, right? It would have been very deep, right? Well, now I'm looking here at a beautiful screen, a 4K screen, just for my computer. It weighs almost nothing, right? And if you had asked someone 15 or 20 years ago about the technology for display screens, well, some people would have been very optimistic, and there were the beginnings. But to get to where we are now would have been hard to imagine. It would have been hard to imagine in the first part of the first decade, 2005, 2006, that companies like Samsung and Apple would produce phones that can do everything they can do just 15 years later. So I see it as engineering and science challenges. I don't see it as showstoppers.
That's great. It's getting we're getting more excited actually. You are IBM is so much convinced that to deliver the real technology to the real market. We have about 3 or 4 minutes, and I have 2 questions. Okay, so
Okay.
One of the questions you mentioned about the material development from chemistry applications, right? Today we have great the worldwide trouble with the pandemic, and do you think quantum computers can also help out the medicine developments, like to develop the vaccine for the COVID-19?
No, not for COVID-19. It's simply that the viruses and the molecules that we are working with are very large, and quantum computers are still modeling very small molecules. And so maybe someday in the future, but today, no. And if you see any company talking about how quantum computers will help COVID, be very careful, because it can't.
Yeah. Another question is, so the IBM has been the technical leader in many areas. Well, for example, the classical computers, IBM was the first one to build the commercial classical computers, and has been the world's largest company until 2000, early part of the 2000. And in the quantum computing technology, the development is another one. But if I look at your R&D investment, it seems to me that you have very long-term return, the expectations in R&D investment that is not usual for the commercial entities. What is your vision within IBM, and also how can you convince all business to have such kind of long-term development of the R&D section?
Well, IBM research began in I believe it's 1945, 1946, around then. I was the head of the math department. So just for example there, that started in 1958. So 62 years ago. And the math department, put another way, was started before IBM introduced the mainframes, the early 360s and things like this. And IBM has gotten many Nobel Prizes and National Science Awards, and We lead the world in patents, many of which come out of IBM research. It's long-term research is part of our culture. Now, it is there to support the business, to be very clear. But IBM management, IBM leaders have long recognized that to change the world, to change the industry, to make our customers successful, we must consistently invest in research. And we must have a very dynamic plan, because what research looked like 10 years ago, IBM research, would not be appropriate for what research must look like in 2020. And so we do that. The strategy changes, it is reviewed, it is well supported. I have been with IBM a very long time. To be explicitly, I have been here for 37 years. Now, that may sound like a long time, but people my age have often been, if you add it all up, in many different companies. I just happen to have been in IBM research 2 different times. I ran the software and Linux business. I did mobile, I did Linux, I did all sorts of things. You can do that in a big company like IBM. But ultimately for me, it's the company's commitment to research that has made it so special, and why out of those, well, I will admit is a long time, 37 years, I have chosen to spend 23 of those in total in research. It's a wonderful place, it's an exciting place, and I will tell you that quantum computing is by far the most exciting thing I've ever done in my career. So it's been worth it.
That's great. We wish to have IBM researchers in Korea too then.
Okay. Okay.
Right. So I think we can wrap up the Q&A session, and also I'd like to highly appreciate your presentation about quantum computing on the cloud in the 21st centuries. It was a great presentation and keynote speech. Thank you very much.
Thank you very much. It's my pleasure.
Great.
네, 이렇게 첫 번째 기조 강연으로 문을 열어주셨습니다. 온라인으로 연사를 뵈니까 굉장히 또 신선한 경험인 것 같습니다. 함께해 주신 두 분을 다시 한번 소개를 드리죠. 이준구 카이스트 인공지능 양자컴퓨팅 ITRC 센터장께서 대담자로 함께해 주셨고요. 그리고 로버트 슈터 IBM 퀀텀 총괄부사장께서 강연에 수고를 해주셨습니다. 두 분께 다시 한번 감사 인사 드리겠습니다. 첫 번째 기조 강연이 진행되는 동안에 저도 잠깐 이 생중계 화면을 보니까 정말 많은 분들께서 또 함께해 주고 계신데요. 뜨거운 참석 열기로 함께해 주신 분들께 다시 한번 감사 인사 드리겠습니다. 소중한 의견 함께 나눠주시고요. 최근 과학기술 분야뿐만 아니라 다양한 분야에서 언급이 되고 있죠. 양자 컴퓨터에 대해서 이야기 나눠봤습니다.